The man who's about to speak is probably familiar to many of you, but for anyone who doesn't know him, Clojure is the guy who puts mean and nasty in the Clojure community. Right? He's that guy who's out there on IRC just flaming people, not being helpful at all, just totally viciously abusing folks, along with his compatriot Fogus, also just known for being a terror. In all seriousness, Clojure is a great resource. He was hugely helpful to me when I was writing the book. Nobody would offer any feedback on the macro chapter, and Rich just laughed at me. He said, "Haha, you have to explain macros." And Clojure, over the course of one long evening, went through it and offered a ton of good suggestions, probably holding back only a few things to put into Joy of Clojure instead. Also very excited for Clojure that he has joined the LonaCloud team. If you have not met the LonaCloud guys, they are the purveyors of fine water bottles and also cloud software. And there's a bunch of those guys here, really cool, and they have a rapidly growing Clojure team, if anyone here is interested in working in Clojure. And I have to say on a personal basis that it's definitely at least the second best place I could possibly have been happy seeing you end up. So very excited for LonaCloud and for you. And without further ado, Clojure is going to talk to us about ClojureScript.
Hi. ClojureScript, under the hood. Okay, so as Stuart just said, I'm not at Century Data Systems anymore, as it says in the program. I just started at LonaCloud this week. So feel free to ask me anything you want about that. I won't have the answer, but you can ask. So I've given one or two talks about ClojureScript now. The guys from Chicago will remember one of those. And it turns out that I end up having to say the word closure a lot in a lot of different contexts to mean slightly different things. So what we're going to, well, here's something that I found myself saying recently. This snippet of Clojure causes the ClojureScript compiler to produce a closure in JavaScript that uses a ClojureScript protocol extended to a Google Clojure type. Not only will I get this wrong, but it won't make any sense anyway. So I'm going to try, at least for the period of this talk, to use some slightly different terms that will hopefully be more clear. I will refer to regular Clojure, by which I mean mainly Clojure JVM, the original implementation, although most of the things that I'll say about that are true for Clojure CLR as well. I will try to refer to ClojureScript as CLJS, because it sounds more different, and then G-Clojure. Fortunately, I don't plan to talk about the Clojure language construct or Google's compiler, so we can just leave those out for now. All right, so here is what I want to talk about today. There's a lot of cool things going on, people using CLJS in interesting ways. I've heard a couple stories already. I know there's other things going on out there. I'm afraid that this is not going to be a slick demo or even an overview of CLJS as a whole. There are some tutorials. Mark McGranahan wrote a article recently that's great for sort of getting your feet wet, getting you started, giving you a good overview about how it works at a higher level and how to take advantage of it. What I was hoping to do is something more in-depth here. Unfortunately, we don't have time to do a complete study of the entire system. So instead, I'm going to try to take a narrow dive here, starting with the data types and digging on down through the protocols that undergird those, the macros that are used to generate the protocol code, and then, if we have time, we'll look at the compiler underneath that. So it's not a broad survey, but it's hopefully a cohesive, narrow dive through some of the guts of ClojureScript itself. The one thing I struggled with this talk is trying to find some way to tie these concepts together. I drew a pyramid. The way the different layers interact with each other isn't really analogous with each other, so it's just a visual aid here, so don't read too much into that. Okay, yeah, we're going to start by looking at data types. Here are 3 of the collection types that have literal syntax in CLJS. There's one other one I left out. Which one is that? You speak up? List, yes, list, of course. I left out list because I didn't want to talk about it. So here's a vector, and this is actually the ClojureScript vector implementation. CLJS core vector, and it's a data type with 2 fields. Metadata field for holding onto the metadata that you need, and the other is a regular JavaScript array. Simple JavaScript array. So it's very lightweight to create these things. What it means, though, it's much less complex than the regular Clojure vector, right, which has structural sharing and things going on. Currently, in CLJS, we don't have that. So this is essentially copy on write in order to provide the semantics we expect from a vector. So any change, if you use assoc or conj or anything on a CLJS vector, you'll get a whole new JavaScript array and a new CLJS vector around it. Okay, now let's see if I set this up right. Hopefully, we can actually try this out. Can you see the bottom, the top part of the bottom pane there as well? In the back? Okay, good. You can't? Not even the top part? I'm sorry, right here it says regular Clojure REPL. Can you see that line? Oh, is it too small? Is that the problem? Let me try making it larger. It's scary. Okay, that's going to mess things up, but we'll go with it anyway. Okay. Is it getting cut off on the side too? All right. We will try to make do. I'm sorry about that. Okay, so what we've got here on the top is a regular Clojure REPL, but it has loaded up in it the CLJS compiler and environment stuff so that we can interact with it. So we're sort of poking at CLJS from the outside. And here's a little macro. I will try to scoot it up there. Little macro called JS that I wrote for the talk. It's based on code that Rich had in the original implementation. And it just takes a form and prints out what the JavaScript equivalent of this is. So we can see what one of these vectors actually looks like when it gets compiled to JavaScript. So there you can see it's calling the from array function of a vector object. And here is that literal JavaScript array that we were talking about. Right? So this is not a vector here on the inside. This is JavaScript code. So this is a 3-element JavaScript array. And you can see that the ClojureScript expression for 3 plus 4 got compiled right in there. All right? Simple enough. Makes sense, right? Okay. So that is, oh, that's right, vector. The next one is map. In CLJS, we have two types that implement maps. In regular Clojure, of course, we've got several that are used in various ways. Array map, hash map. CLJS doesn't have any of the sorted collections yet. But the reason we have these two implementations is specifically so that one of them can take advantage of what JavaScript engines are good at. So objmap is specifically to handle CLJS maps whose keys are string-like. And what I mean by string-like is strings, keywords, and symbols. So as long as your CLJS map has keys entirely made up of those, you will be using an objmap underneath. So you can see this one has a few more fields. We've got, again, the metadata field. We've got an array of all of the keys that is useful for iterating, since in JavaScript it's hard to correctly iterate through an object. And then we have the stir object. I'm sorry, did I say 4? There's 3 fields there. The string object there is a object that holds exactly what you would expect for a map. The keys are the strings of the original objmap, and the values are the actual values that you stored in it. Again, this is copy on write. If you make a change, you assoc or something, you'll get a whole new objmap, a whole new keys array, and a whole new stir obj. The reason that we have hash map is because CLJS, like Clojure, promises that you can put other things in keys in a way that JavaScript doesn't handle in its objects, right? You can put numbers, you can put other collections in there as keys. And so hash map does more complex things in order to store those correctly. The hash obj there ends up being a JavaScript object with keys that are hash numbers, and the values are like a bucket of the key value pairs. So both changing and looking things up in that is a little bit less efficient. So let's take a look at that. So here's one that has just keywords as keys, right? So we ought to be able to see what that produces. Okay, so there's some interesting things there, right? We've got the obj map. So this part is similar to vector, where we have an object that's holding essentially what we're treating as a static method. It's a function, right? From obj. So here are the two fields. One is the list of keys, or sorry, the JavaScript array of keys. And here is the JavaScript object of the key value pairs, 2 and 5. Now, those question marks are my terminal's attempt to print the crazy Unicode character that we put at the front of a string in CLJS to separate keywords from strings. There's another one that unfortunately prints exactly the same way for symbols. But that way there's no collision between keyword strings and symbols. Now down here, we've got a similar looking map. But in this case, the CLJS compiler doesn't know for sure, can't tell at compile time that this expression is going to be a string or a string-like thing. And in fact, it's not, right? It's going to be a number. So if we look at the JavaScript for this, we will see that the compiler chooses a hash map instead. And the parameters there are a little different. Here we have two arrays of things, keys and values. So from arrays in this case acts a little bit like zip map to build up the object. Okay. And finally, set. Just like in regular Clojure, CLJ set is built on top of the language's own map type. So here we just have a CLJS map. Currently, it's always a hash map. It doesn't use the obj map ever in a CLJS set. Okay. All right, so those are some of the data types that CLJS provides and a little bit about how they're implemented. It may be worth noting that those are all implemented in CLJS itself. There's CLJS code that implements those using def type. In an early version of this talk, I was going to walk through all that, but then we don't have time for more fun stuff later. So what we do have time to look at, though, is how protocols undergird all of those data types in CLJS. In regular Clojure, what we have instead are interfaces. So let's take a look at that for a moment here. So along the top there are some of the CLJS data types. You can see I added list. And then down the left are CLJS protocols. The protocols have the same semantics as they do in regular Clojure. And then each of those X's indicates a implementation of that data type to that particular protocol. So you can see that Assoc, I-associative things, are provided for vector and map, but not for set and list, right? Collections, counted, all of these of these types are collections and are counted and can be emptied. Then you can see I-indexed is only for vector, and I-map is only for map, and so on. Okay, so this is actually somewhat similar to what you would see if you were to build a similar chart looking at regular Clojure's interfaces. You could have types along the top and interfaces down the side. One of the differences is that here there is no inheritance at all. This is a flat list in CLJS. But there's another difference, and that is what some people might call the expression problem. If you take well, actually, it's very interesting. Somebody earlier, I believe it was Stuart Sierra, was talking about how what interfaces you have to implement if you are creating your own collection type in regular Clojure, right? Well, here I'm looking. I've got that label Goog map there to indicate a G-Clojure map type. Okay, the G-Clojure library provides its own map type. I'm not sure why you'd want to use it, maybe for interop or something in ClojureScript. in CLJS. But if you're handed one of those, in regular Clojure, you have similar problems where you might have a map coming in from, again, actually Google has a collection library for Java, right? And there's some other ones. Apache has some. So if you have a class that you didn't write, and you have interfaces in regular Clojure that you'd like it to implement, you're stuck. There's no way to do it without writing a wrapper or some other kind of construct. But because we're using protocols, because in CLJS, protocols are already what's being used for the internal types, we can take some class that we didn't write, googmap, and extend it to CLJS's own protocols and make it work. So let's take a look at how that will actually, how we can do that. Okay, so what we were looking at before here was a regular Clojure REPL. It really is getting, let's see if I can not cut off quite so much. What we were looking at before was a regular Clojure REPL, right? So what I'm going to do now is I'm going to set that aside here for a moment and instead look at a CLJS REPL, right? So before we were poking at the language from the outside. Now we are inside a REPL, inside of CLJS. So what we type here is actually going to be ClojureScript code. Okay, so first I'm going to bring in the Google structs library. Okay, and then create a instance of one of their maps. So because it's a map, we can call a get function on it, right? No, you can't, because get is a CLJS function that expects a particular protocol to be implemented. And if you look at the error that's actually thrown, you can see that it's talking about it right there. Sorry about the wrapping. I didn't realize my text was going to be too small. You can see right here, it's trying to call the iLookup protocol's -lookup method. And it says it can't find it. That's what get does. Get is defined in terms of this protocol, and it doesn't know how to do it. So if we want it to do that, we've got to tell it how. And this is the entire implementation for that. We're going to use extend type here, refer to the name of the class we want to extend, or the type rather, and the protocol we want to extend it to. And then here's the implementation, right? We're just going to call a method of the actual googmap and the key that we want it to look up. So if we run that, now we can do that same get on M, and it will look it up. Now if you notice, I did not create a wrapper. I didn't recreate the original googmap object. That object was live and still sitting there, and I changed the definition of, or the extension of that existing protocol to that existing class and instance, and it just works. You can also see that keyword lookups work because CLJS uses the same protocol for that as well. Because I used name in the implementation right here, this is a design decision, right, where I decided that for this particular extension of googmap to iLookup, that I was going to translate all of the keys into strings. So if it was a keyword, I'm going to treat it as a string and look it up in the map there, right? Okay, and then there's some other ones. I had some other X's in that chart. So here are some implementation to make those real. Making googmaps iSeekable, associative, and printable. If we combine all those together, now we can actually have a useful printout of a googmap instance. And I did it associative by pouring the existing Goog map into a regular Clojure or CLJS map. And so that works as well, but you can see that the type has now been switched underneath to a regular CLJS map type. Okay. There was something else I wanted to say about that. Oh, right. So, when we're looking at protocols, whether in regular Clojure or CLJS, it's important to pay attention to who owns the types and the protocols that you're working with. In this case, I'm taking, as I said, a type I don't own and a protocol I don't control and hooking them up. The problem with that is that in an entire running system, there's only one of these cells for each combination of Goog map and say iLookup. So for example, I had that name call in there, basically saying it's impossible to look up an actual keyword or symbol in a Goog map because I think there's probably only going to be strings there. If I were to put that code, that extend type call, into a library and somebody else were to do the same thing and make a slightly, especially if they were to make a slightly different decision about how to implement that, we'd be in conflict. So, if you own the data type, or you own the protocol, if you've invented the protocol and you're extending it to a bunch of types that are out there, or if you create a new collection type and you're extending it to existing protocols, you're safe. But anytime that you aren't in control of either one, you have to follow a kind of golden rule, right? And make sure that you are willing to either back off if somebody else does it, or fight for your right to be the correct implementation, right? So you have to be aware of that, and there's a real composability issue that we have to be aware of. I think a good rule of thumb there is to avoid putting that kind of thing in any kind of low-level library, such that it might show up without people intending it. That's something, if you really need to combine two things that you don't own, it should be a high application level thing where people aren't going to be reusing that code in ways that you weren't thinking about. Okay. Okay, so we used extend type there. Extend type is not a language primitive in CLJS. It is a macro. So we need macros in order to get protocols the way we do. And in order to talk about macros, I need to review a little bit about the REPL. And you probably can't see that in the back. And there's nothing I can do about it. We'll zoom in anyway, though. So, right, we know about this, right? The read, eval, print loop. This is familiar. I want to look a little bit closer at eval to see what's going on there. Anthony touched on several of these points. But in the regular, both CLJS and Clojure follow the same pattern for what goes on in eval. You can split it up into these 3 steps. The first being analyze and macro expand, which happen in an sort of interleaved way. The result of that is a tree with a lot more information about the code that was passed in originally. If you are familiar with what an AST is, you would find this tree to be rather familiar as well. Emit consumes that tree and produces whatever the target is. So in CLJS, that's JavaScript. In regular Clojure, it's bytecode, either CLR or JVM bytecode. Once that's been emitted, then we've got to actually run it somehow, right? Because this is eval. We can't just have produced the code. So in eval itself, in CLJS, it's a little bit pluggable, right? We can either load it into a Rhino instance and run it inside the same JVM, or we can send it over the wire to a browser. There's different things we can do with that. So I want to take a look at some of these steps individually and see exactly what CLJS does. In order to do that, I'm going to switch back to a regular Clojure REPL. Okay, so first let's look at reading. Here I've got a string version of that very same code that we saw earlier that's extending iLookup to Google's map, Clojure's map. Right? And then I'm going to read that and put the result in a form. So that's just a messy way to quote it, right? So now we can look at the form and see that it's exactly what we would expect. So what's the difference between this and the string? What is the type of value that's in form right there? It's a list. Very good. So it was a string, and now it's been read into being a list. Now, macro expand is something that a lot of us are familiar with. I have to mention the env here that CLJS uses. This is the compile time environment that is being used. That contains information like what namespaces are available, what vars have been defined in them, what the current namespace is. We'll see it in a moment here. I've got a little one mocked up for this example. So in CLJS, when we use that, then that describes the environment in which the form is going to be macro expanded, and we can see the result of that. Except I forgot to evaluate it, so let me do that quick. Look, there it is, env. There's the current namespace and the context and the locals. Let's see if that'll do it now. There we go. So that's what the extend type macro is actually doing. It's going in and poking at the Goog map prototype and using namespaced attributes here to actually put the implementation right inside the object. Okay, so I said that macro expand and analysis sort of happen intertwined a bit. And so once we've macro expanded, we can see what is going on already inside to analyze. But this is going to do the full analysis, and we're going to get to see the entire AST, which sometimes can be a little bit verbose. I don't know if you could see. Oops, sorry. How much it goes on a bit there. And a bit more. So for the rest of this, we're going to use a slightly simpler form. Let's use aget. Aget is another macro that is available in CLJS. And again, we can look at it after it's been read. We can macro expand it. So now this is another little interesting feature of CLJS, that there's this JS star special form. And this is specifically to allow parts of CLJS itself to drop down to JavaScript where necessary. So what ends up going on here is this is basically just a sort of a string interpolation, so that each of these parameters, after they've been compiled to JavaScript, can be inserted into those two spots. So you can see it's doing, those square brackets there are JavaScript array lookup, right? Because we're doing aget. So let's look at the analysis for that. And this isn't going to fit either, is it? So so this is a little bit smaller. You can see the environment is being repeated here. As it turns out, it's very useful when you're emitting the JavaScript to have access to the full environment. So that's repeated in every node. The most important part is the op. Each node of the tree has an op field that tells you exactly what this particular node is for. This is the JS for the JS star special form. And then down here we have the arguments to it. You can see it's done some work to split up the string interpolation input. And then we have arguments. The first argument was the var. In the example, it was sum-array, and you can see this has now been recognized as a var. It is been fully namespace qualified. It's got the underscore munging going on there. So this is a JavaScript name for the var we referred to. And here we can see the constant 5, the AST for that. So now that we have all that information about the code, we have everything we need to call the emit function from the compiler. So you can notice that the environment was passed in to analyze, but we don't need it anymore to pass into emit because it's been copied everywhere that we need it. So what's going on? So we can emit and see the actual code produced by that example. Okay, now a very important thing to know here is that no JavaScript code has been run yet. So that means all of the macro expansion, all of the analysis, everything that we've looked at just now is all running in the JVM, mostly written in Clojure, in regular Clojure. And so that is the key point about how macros in CLJS are Clojure code, not CLJS code. Because we haven't even sent anything to a JavaScript environment yet, right? So that is how analysis and macro expansion work. But there's another step even below that. That is the compiler itself. The compiler is what actually does the macro expansion and does the analysis. So let's take a look at that. Now, what I intend to do here... Okay, now let's do this first. Let's look at this. There is a feature in Common Lisp called symbol macrolet. Is anybody familiar with that at all? A few of you. Okay. It's different from macros we're familiar with in Clojure in two ways that are both hinted by in the name. One is symbol and the other is let, right? So symbol macrolet, the symbol part means that in order to refer to it, we don't need to have a list that looks like a function call. Normally in macros, you do that and you pass it some parameters. For a symbol macro, all you need to do is refer to the symbol. So in this little example here, this syntax, by the way, is not at all what Common Lisp uses, but this is what's easy to implement in CLJS. So this here is all that is needed. A simple symbol, naming a symbol is all that's needed to trigger a symbol macro expansion. The other part is let, right? Symbol macro let is your hint that this is a lexical macro. So it's just within certain lexical scope. It's not at a namespace level. Okay, so I'd like this to work. The idea being that this could be some expensive work right here in the delay, right, that might take a lot of time, or we might want to make sure we don't do if we don't have to. And then we could have code down here that itself might be either delayed or run in a lazy sequence or in some other way put off. And rather than having to deref the delay explicitly down here, we can have a symbol macrolet so that just by referring to the word speed, we actually get the code deref speed delay. So this part here is the name of the symbol we want to bind. This part here is a sort of automatically quoted expression that will be inserted down below when it comes time to run it. Okay, so I'm now going to open up the CLJS compiler, and I don't want anybody to panic. It's too small. Well, we'll try here. Okay, so I want to change two places. I want to change let so that it understands this symbol macrolet metadata that I have here on the speed symbol. And I want to change how symbols are understood and analyzed, right? So here is the function that analyzes let. And I'm not going to try to explain every line here, but I do hope that you can get a sense of what's going on and that you will find it unscary enough that if you feel like poking around in there, you'll be able to do that. So this loop right here is going through all of the pairs of bindings in the let expression itself. Remember, this is compile time, right? So we're going through the pairs of symbols, or rather the symbol and initialization that we put inside the square brackets of a let. So you can see here it's getting destructured. There's the name of the symbol we want to define, and here's the init expression. Okay, you can see it's checking some things. All right. So this block here is the code, the original CLJS code that you would find in the repository today. You can see it analyzes the initial expression to figure out how it's actually going to do that, right? Because that gets run at runtime. So it has to analyze it. And then it loops on these three parameters. The first is building up a stack of binding environments. The next one stuffs the binding environment into this larger environment object that we're building up, the one we passed in that continues to get built up as we compile. And then we go on to the next pair of bindings. So those are the three things we've got there. So what I've added is these three lines right here. So what I'm doing is I'm checking to see if the metadata for the name has symbol macrolet on it, which for this one here, for this line it does not, right? That's a regular let. This one, it does have the metadata. So in that case, we will switch to this branch, and we leave the stack of the binding environments alone. We still go on to the next bindings. So the only thing different is this one right here. And so what we're doing is we're putting into the local environment this little map. It has symbol macrolet true so that we can find that later. And then it just copies right in the original init form, unanalyzed, right? So that's our automatic quoting. We're just dropping that form straight in. That's everything we need to know in order to jump down to analyze symbol. Analyze symbol normally is going to first look to see if it's in the locals. Right, this is the same binding environment we just modified. So if it's not in there, then it skips down and does var resolution, looks around in namespaces to try to find what global var that might be. In the original code, CLJS just went to this then. If it wasn't a namespaced var, or a var that could be, if it could find it in the locals, right? This is if we did find a local binding, LB local binding. If we did find a local binding, then we were just going to produce one of these. So I added these two lines right here. These two lines right here. So it checks to see if that symbol macrolet field that we put into the binding environment, if it's true, then rather than making a var, we at this point recursively analyze that form that we set aside. So it's just as if it were textually right here. We're going to analyze it right at this point. So between those two, that is all you need in a CLJS REPL to be able to do symbol macrolet. So okay, so if this works, what value should this produce, right? We've got a delay of 5 here. Down here we're saying 10 plus speed. Speed itself is going to be expanded into dereffing that delay, so it should be 15, right? And it works, 15. So by adding, 5 or 6 lines to the CLJS compiler, we were able to add a feature to the language that CLJS hasn't had before now. Okay, so that's everything that we talked about. We started up at the runtime and compile time representations of data types. We looked at the protocols that implement those and why it's nice that CLJS uses protocols for its own data types rather than using interfaces like regular Clojure. We looked at how macros are a fundamental part of making protocols work and how the compiler does some of its analysis and compilation. And I don't know when I'm supposed to be done, but that's all I've got. So are there any questions?